Hello, my name is Bradley Van Dam, and this will be Physics 2 exam chapter 22 workout. And I will be doing question number 1, which is 22.4, and then there's 4 different parts of it. So let's get started. So part A gives us an example that we're going to use for parts A through D. So I'll just do 1. So it says an imaginary cubical surface of side length L, or of side L, has its edges parallel to the XYZ axes on one corner at the point x equals 0, y equals 0, z equals 0, and the opposite corner at the point x equals L, y equals L, and z equals L. The cube is in a region of uniform electric field of E equals E1I plus E2I, or E2J, where E1 and E2 are positive constants. Calculate the electric flux through the cube face in the plane x equals 0 and in the cube face in the plane x equals y. So for parts A, B, and C, we're going to be calculating the electric flux through cube face in the plane x equals 0. So for A, I'll say x equals 0 and x equals L. And then B is y equals 0, y equals L. C is z equals 0, and then z equals L. Okay, so let's first draw this out. Actually, and it has a part D. It wants to know the total electric flux of the cube. So that's the last part. So we're given all this information, so let's just draw it out. So we have cube, and the cube is like this. So this is going to be point L, 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 right there. And then this point of origin is going to be 0, 0, 0, which is each of these specific cases. So it wants us to calculate electric flux. So here, x equals 0, then x equals L, so L 0, 0. And then part B is 0, y equals L, and 0. C 0, 0, L. Okay, so we have to find the electric flux through each of these cube faces given different conditions here. So we know that electric flux is equal to E times A. So that's the that's the area right there. So we are given in the problem E, the electric field E, is equal to E1 I hat plus E2 J hat. And that's going to be equal to 0. And then we have to, for both cases, we have to solve for A. So A is going to be the area. So in this case, L, and then times the lowest x value, so that's the 0 there, so that would be the little vector, so that's going to be negative I hat, and let's see here, yep, so we take the electric flux equation, electric field times that area, which we have here, so we can say for electric flux x equals 0 equals and then we have L times negative I hat, which is just negative L I hat. We're multiplying since they're both I hat, plus E2 j hat, but since there's no other j hat component to multiply by, we just have 0, so multiplied by 0, which goes to 0 there. And then we have our final solution for x equals 0. So for the electric flux of cube face where x equals 0, we have, multiply this all together, we have negative E1 L squared. Yep. Okay. And then we just, so in this case, so for the x equals L, we are, since we're now taking that largest value, we're going into the positive x direction. So now x equals L, we have, again, E1 I hat times, and in this case, it's going to be positive since it's now going for the highest value, or for the greatest value of the x. So then we have L I hat, and then again, this is still going to be 0, so I'll just write 0 there, equals, so then it's going to just be E1 L squared. Yep. So that is part A. Part B. And again, we just do kind of a similar approach here. So y equals 0. That is, so in this case, it's now not going to be I hat, it's going to be j hat since we have y equals 0 here. So instead of there being no other component for the j hat to multiply by, it's essentially going to be, let's write it out here. So it's now going to be E1 I hat, but now there's no other I component or x component here, so that's going to be multiplied by 0, which then is equal to 0, plus now E2 j hat times negative L j hat. So instead of negative E1 L squared, we're going to get negative E2 L squared. And that's for L equals 0, but if we do L equals Y, it's a similar process here. So we have electric flux, Y equals L is equal to, so we just, instead of E1, it is now E2 j hat times positive L j hat E2L squared. And so for part C, since the given electric field only has I and j components, it doesn't matter what we do in this case, both instances of x equals 0 and x equal L will give us an electric flux of 0. So we, again, just kind of observing the problem based off of the electric field they gave us, we don't even have to do any math here since there's no other, I guess, z component in this electric field equation. So we can just, without doing any math out here, we can just conclude that for part C, we can say for both z equals 0 and L, that will be equal to 0, 0, again, based off the reason I just explained. Okay, and so for part D, it wants us to find the electric flux of the entire cube. And so since we now know that the electric flux for z equals 0 and z equals L is 0, and we already know the electric field is equal to this right here, which is equal to 1, or I'm sorry, equal to 0, we essentially have Ex, Y, Z, and we already know that both of those equal 0, so that's going to be, this right here is going to equal 0, and we again found 0 for EZ, so it's 0 plus 0, so essentially the entire electric flux of the cube is just going to equal 0. So I'll just say cube equals 0. Okay, so that is all of the 4 parts for 22.4.1. And now we go to so that was more of a conceptual question. So this problem, for parts E, F, and G. So the problem asks, or gives us a point charge Q is at x equals 0, y equals 0, and z equals 0. And an imaginary hemisphere surface is made by starting with a spherical surface of radius r centered at the origin and cutting off the half in the region z greater than 0. The normal to this surface points out of the hemisphere away from the center. And it wants for part E, so E, to calculate the electric flux of the hemisphere. So I'll just do, and then half sphere, given point charge Q equals 9 nanocoulombs and radius, or R equals 0.1. So in this problem, so we can just draw it out for understanding. We have semisphere and a normal, and yes, so z plus 1, or z is greater than 0, sorry, for the hemisphere, which is why it's above the z-axis, and then y. So we want to find the electric flux of the semisphere given these two conditions. So we can use the the general Gauss's law. So the electric flux is equal to Q enclosed over constant. So we're looking for this. And again, this is for the half sphere. That'll be important, the fact that it's a half sphere. So plug in all the information. 9 times 10 to the negative 9th coulombs divided by that constant, which is 8.85 times 10 to the negative 12th. And that's going to give us, let's math out here. It's going to give us 1017, but that's for assuming it's a sphere, but we're only doing a semisphere, so we have to take 1017 and divide that by 2, and then we get 508.2, or sorry, 508.5. I'll just leave it 508, and that is in Newton meters squared per coulomb. Yeah, so the fact they gave us a hemisphere, we had to divide this value by 2. And so we get 508 Newton meters squared per coulomb. And so for part F, it wants us to do the same thing, but given a point charge Q equals negative 8 nanocoulombs and R still equals 0.1 meters. So we do the same process here. So using that same equation, we now just do negative 8 times 10 to the negative 9th over the constant equals, and so we can just use the same negative 8. We get 903 point, we can just say 904, so we get 904, and then divide that by 2 is 452, and again, almost forgot to incorporate the negatives. That is negative 452, same units for electric flux, Newton meters squared per coulomb. And part G asks us, again, similar ask. This time we're given the same point charge, -8 nanocoulombs, but this time R is equal to 0.2 meters. And so let's see here. Yeah, so originally from the problem, let me see, I'm missing some information here. Oh, no. Yeah, so we actually don't need to do any extra math here, because since we calculated this value of the -0.8 nanocoulombs from part F with a R equals 0.1, but this time it's 0.2, that's going to be outside of the radius of the sphere given from the problem. So we can say for both F and G, since 0.2 is outside the radius, we can say that it is also equal to -452. So let's just do F comma G, circle that, and then this is the answer for part E. So that was 0.2. Okay, next problem. So for parts H and I, we were given the information: an imaginary cubical surface with side length 5 centimeters or 0.05 meters has a point charge of 6 nanocoulombs at its center, and it wants us to calculate, for part H, it wants us to calculate the electric flux through the entire closed cubical surface. Excuse me. Okay, so part H. Flux cube if the cube has sides length 0.05 meters and point charge, I think it said at its center is +6 nanocoulombs. Okay. So we can still use the same equation for electric flux. This time it's for a cube. Is equal to charge enclosed by the surface over that electric constant equals, so we have initially the 6.0 nanocoulombs, so 6, 10 to the -9. I'm just converting this to coulombs as it is instead of nanocoulombs. And that is going to be, again, divided by that constant 8.85 times 10 to the -12th equals, I'm just going to go back instead of retyping the whole thing out. It's not negative, and then we got 677.9, so we can round that to just say 678 Newton squared per coulomb. And that's for the entire cube. So that is for part H. And part I wants us to calculate it, but only through one of the 6 cube faces. So I'll just do this, and then I'll say one face. One face, question mark. So essentially we just take the value that we got here from part H and we multiply that by 1/6, since there's 6 sides to the cube. We only want to know for one out of those 6 faces, and then we multiply that by the electric flux calculated. 1 times 678, and that is 113. So that is the electric flux for just one out of the 6 cube faces. That's part I. And then the last one, do I want to, I'll just do it on a separate page. Okay, so this one has another 3 parts, so J, K, and L. So the problem is that there's an imaginary spherical surface with a radius of 5 centimeters or 0.05 meters, similar to the past problem. And then this is centered at the origin, so X, Y, and Z equals 0. And then we want to calculate the net electric flux through the surface if a point charge Q1 is equal to positive 3 nanocoulombs at a specific location, which is X equals 1 centimeter, Y equals 1 centimeter, and then X equals 0. So for this, the problem is asking, and this is, part J. So J wants us to find flux if Q1 equals, and then I'll just do at, I'm just going to convert this to meters. So 1 centimeter in the X and the Y position is just 0.01, 0.01, and then Z equals 0 meters. Okay, so since we're given multiple components here, we have to make sure that the distance of the point charge from the origin is less than or equal to the distance of the object containing them. So what we can do is we can just use the distance formula, and I'll say, since Q1, I'll just do D1 equals, and then the square root of those values, so 0.01 squared plus 0.01 squared, and then plus 0 squared is just 0, and then that will give us 0.01 0.01414. So I'll just say, just for the sake of proving that it's within I'll put up again here. So sphere, I'll say R sphere. They said originally was 5 centimeters, and I'll just convert that to meters since that's what I'm doing for the rest of the problem. So we have to make sure that these distances are less than or equal to that value of 0.05 centimeters. So this one is 0.01414 ... So that checks out. So we can now go to calculate the electric flux given this information of point charge Q1. So let's see. So we can still use, again, instead of just saying Q enclosed, I'm just going to say Q1 just so I can keep track of it, of the point charge I'm using, and then the constant E naught, and we're looking for flux. So we're given 3 nanocoulombs divided by, again, the constant, 8.85 times 10 to the negative 12th. Actually, we can probably go back to what I did. Yes. So then we get 338.9. So let's call that 339 Newton meters squared per coulomb. That's J. Which one is that? Part K gives us a new point charge in a new location. So we're now given, again, still to solve for electric flux. So but given Q2 is equal to -8 nanocoulombs, and then at position, they give us 2 centimeters by 0 by 4 centimeters. So that is 0, 2, 0, 0.04 for centimeters. And I'll write part L up here above that. So again, similar process. We have to make sure that point charge is within the object that's supposed to be containing it or enclosing the charge. So D2, take those values and just square them, or square root of those squares. 0.2, 0 is just 0. Second, squared, and that is just barely less than 0.05, but nonetheless it checks out. So that's 0.0447, which is less than 0.05, so that checks out. And then we just do the same process, but now we use Q2 instead of Q1. So -8. Again, a little repetitive, but the main thing is just checking to make sure that it's inside the sphere. Nope. .903. Did I do that right? No, I did not. I forgot I have to do not just Q2, but I have to add both the charges there. So, because again, it's all the charges that are inside the object now. And so they incorporate another one. So that's Q1 plus Q2. So that's not -8. That I was about to say, I was like, that number, that didn't sound right. So we have to do essentially the 3 nanocoulombs plus the -8 is just going to be -5. So we can say, instead of -8, we can just say 5. Okay, yeah, no, that sounds about right. So yeah, so I almost forgot. You have to, I'll write it more clearly. Since they're incorporating another charge, Q2, you don't just do that one by itself. You have to, it's still part of contributing to the electric flux. So we add those together, and that's what gives us the -5. And then that gives us the -5.6, let's say 565, just to round. Okay, and last part of the exam, so it says Q3, so now we're given Q3 is equal to +2 nanocoulombs, but this is at 0.04, -0.02, I'll write it up here, and then 0.03. So again, we have to verify that Q3 is there. So let's just do distance 3 or D3. And it doesn't matter that this is negative, it's going to get squared. So I'll just add them all together. So 0.4 squared, 0.2 squared, 0.3 squared. And again, we have to make sure that's less than or equal to 0.05. So square root 0.04 squared Yep, and you see here, so this is actually outside of the scope of the sphere, so it's outside the radius, so that's not going to contribute to the electric flux of the sphere. So since that is 0.53 ... that is not okay, because it is greater than 0.5, which is the radius of the sphere. So that's not going to contribute anything. So because of that, the electric flux of the sphere is still going to be negative 565 Newton meters squared per coulomb. So for parts K and L. It is going to be that value. And that wraps up the exam for Chapter 22. I hope you enjoyed.